Pluto, having lost its planet status, it would seem that Pluto was no longer on the scientists' minds. Now just a lifeless, frozen piece of space rock on the edge of our system. But over the last 7 years, just like the icy moons of Jupiter, Pluto proved that it is worthy of attention in the status of an object of interest. Among the most unique features of Pluto in the entire solar system: snow that burns, an ocean full of water, a source of heat within the planet, cosmic smog in the atmosphere, ice mountains, and a bubbling nitrogen glacier. This is just a fraction of the incredible discoveries on Pluto, because, as it turns out, there's a possibility of life on Pluto. Thank you. Although it was discovered relatively long ago in 1930, it remained a mystery for a very long time. Even then, it was clear that this planet, due to its remote location and small size, would require face-to-face time. Take a look at the best picture of Pluto taken by the Hubble Space Telescope in 2006. This was the best we could do, and yet it's difficult to see anything concrete in this collection of pixels. Not long ago, the meeting with Pluto finally happened. But first, let's examine what we already know about Pluto before this visit. Let's bring our attention to the fact that Pluto has 5 satellites. The closest and biggest one, Charon, does not actually orbit Pluto, but instead, they move together. Pluto and Charon are even sometimes referred to as a double planet. They orbit the center of gravity between them. This is the only pair of objects in the solar system that interacts in this manner. This is what that looks like. As we take a closer look at the movements of another satellite, Nix, it turns out that the other moons of Pluto move in a pretty chaotic way, which is also unique for the solar system. The New Horizons mission, which commenced in 2006, planned to visit Pluto and take the first proper photographs of it right from its orbit. It appears that Pluto was not in the mood for guests, and at the most crucial moment, the connection with the probe was lost. Thankfully, there's nothing mystical here. The probe system simply wasn't able to withstand the number of commands received from Earth in regards to the maneuvering and photographing the planet, so they shut down and switched control over to the reserve computer. You can only envy the enthusiasm and perseverance of scientists. And after 3 sleepless nights trying to reboot the probe before it approaches Pluto, it was a success. The probe began to orbit Pluto, and soon we received these images. And these images were able to see ice mountains, some reaching 2.5 miles. There was also a large number of craters, which is normal since every object in space is subject to being bombarded by asteroids. Did you spot the most unusual thing about these photos? This white area at the center of the planet Pluto, once dismissed as a mere frozen rock in the outer reaches of our solar system, has captured the attention of scientists in recent years. Its most intriguing feature, nicknamed the Heart of Pluto, pulsates with life. This region is believed to have formed relatively recently in cosmic terms, from a collision with an object about 125 miles in diameter a few dozen million years ago. However, what sets this birthmark apart is its remarkable lack of craters, unlike the rest of Pluto's surface. Instead, the area appears smooth and pristine, indicating a geological activity that filled the impact crater with the white substance nitrogen. This heart of Pluto, as observed by a spectrometer, is composed of nitrogen, the same substance found in the snow-capped mountains photographed by the probe. This raises questions about how nitrogen, which typically exists in a gaseous state, at such low temperatures, could form a liquid and fill the crater. Scientists theorize that Pluto may harbor a warm core beneath its icy exterior, possibly even hosting an ocean of water beneath the surface. Further examination of the nitrogen ice revealed a surprising phenomenon: bubbling. Over thousands of years, the ice bubbles and cracks, indicating heat escaping from beneath the surface. This convection process, akin to the movement of heat within Earth's atmosphere or on the surface of the Sun, provides insight into Pluto's internal dynamics. Another puzzling feature on Pluto's surface resembles a volcano, complete with volcanic activity-like textures. Yet, instead of molten lava, this volcano ejects water. How can water flow on a planet with surface temperatures as low as -400 degrees Fahrenheit? The answer lies in a simple chemical solution, water mixed with ammonia, which lowers its freezing point. This allows water to flow as a thick paste, resembling lava under Pluto's frigid conditions. These discoveries challenge our understanding of planetary geology and heat dynamics. While Earth is warmed by the sun, Pluto's internal heat sources drive geological activity, shaping its unique landscape. As scientists continue to unravel the mysteries of this distant world, Pluto proves itself to be a dynamic and enigmatic celestial body worthy of further exploration. Although the sun heats our planet to a certain degree, it primarily heats the surface. This heat doesn't penetrate much deeper, even though the solar radiation does reach the inside of our planet. It's precisely the presence of a large amount of radioactive and heavy elements at the core of the planet that causes the geological activity and creates the heat within the planet. The scientists assume Pluto would be different. For starters, it's very far away from the sun. Before it was demoted, it was considered the furthest planet of the solar system. The size and density of Pluto also did not indicate the presence of radioactive or heavy elements that could accumulate this amount of heat. The last issue when it came to understanding the temperature on Pluto was the fact that its modest size prevents it from retaining heat. But Pluto proved everyone wrong. So how is it possible for the heat to remain on Pluto? The substance covering the surface of the planet turned out to be more than just ice and snow. It looks like ordinary snow. It's as cold as ordinary snow. But if it were exposed to fire, it would burst into flames. What makes the snow so special? At the temperatures of -375 to 400 degrees Fahrenheit, the water crystals trap a large amount of methane molecules like a blanket. This substance shields the warm radiated part of the planet from the cold surface and influence of the cosmos. This is how Pluto is able to retain heat. Let's move away from the surface for a minute and take a look at this image. The blue haze that you see is Pluto's atmosphere, full of nitrogen. Sure, its atmosphere is not exactly appropriate for habitation because it's mainly composed of nitrogen and has a fairly thin consistency. It doesn't retain heat, and we wouldn't be able to breathe here. Studying the atmosphere, which stretches to 125 miles above the surface, the scientists noted that it has a precise structure and is filled with something resembling smoke. This haze prompted intense arguments, but further research determined that it is not smog. But why would there be smog on Pluto? Turns out, there's something else in the atmosphere aside from nitrogen, carbon monoxide, and methane. We're used to the fact that on our planet, smog appears in connection with some form of a burning process. Some of it happens as a result of human activity, but Pluto has no cars and no breathing living life forms. Or does it? Continuing their research, the scientists tried to recreate the composition of Pluto's atmosphere here on Earth to understand what causes the smog by comparing the causes of smog on Earth and conditions on Pluto. Scientists quickly came to the conclusion that this smog is caused by the way the sun's rays affect the gases in the atmosphere. They make the gas molecules break down, transforming them into soot, which subsequently turns into the haze of smog as it spreads through the atmosphere under the influence of gravity. This soot falls to the surface, turning into rain and giving the planet its signature brown-red hue. The more sunlight the surface is exposed to, the more red it appears. But the most amazing discovery was the nature of the aforementioned soot. Let's briefly come back to Earth and rewind time to 400 million years ago. Back then, our planet was a water world, with never-ending rain and thunderstorms raging above the surface. The composition of its atmosphere at the time was similar to present-day Pluto. At that moment, the sunlight triggered the same processes as it currently causes on Pluto. In the atmosphere of ancient Earth, breaking down from gas molecules, and forming into new, more complex elements, or what we now refer to as the organic basis of life, nucleobases. The particles that will go on to form the first chains of nucleic acid and subsequently DNA and live cells, the basis of life. And right now, these elements are falling from Pluto's atmosphere onto its surface in the form of rain. What's more, these elements get into the cracks and, in the process of cryovolcanism, they make their way under the surface, the place that, as we already know, has plenty of heat. Does that mean that this is enough for a life form, however primitive, to emerge underneath Pluto's surface? It's very possible because the icy blanket is hiding an ocean. Upon studying the breaks and craters on the surface of Pluto, it became clear. The organic matter does not only make its way under the icy surface, it also rises to the top of it. Take a look at this photo. The red streaks stretching from the places where water mixed with ammonia erupted to the surface tells us that plenty of organic matter already formed underneath the surface. Not one is even considered that life on Pluto is a possibility. However, we can already see that this planet is not only geologically active and alive. It has enough heat and is able to retain it under the influence of the sun. A sufficient amount of organic basis for life is formed in its atmosphere. Evidently, there are areas underneath the surface warm enough to contain water. In its liquid form, water mixed with ammonia that burst out from the depths of the planet through the volcanoes we've seen earlier suggests that such areas under the surface are fairly ample. All of this is making scientists examine each new picture of Pluto with keen interest. And after the icy moons of Jupiter, it was Pluto that became the new focus of their interest in search of extraterrestrial life. Having sufficient potential for life to form, Pluto managed to prove that even having lost its status as a full-fledged planet and being demoted to a dwarf planet, it is still very much alive. Mars, the possibility of colonization of other planets, is a matter that has been on people's minds for many years. In the future, once we can travel through space, we will move forward from one world to the next, inhabiting them with new life along the way, and changing these new planets to resemble Earth. Imagine hundreds or even thousands of planets colonized by humans. Life would bloom along the trajectory of our journey through space, and eventually, the galaxy will be filled with beautiful Earths. But how can we achieve a result like that? Just like in any major project, we have to start small. Could you imagine that in the next decade, humanity might start the colonization of our solar system? Today, we're heading to a neighboring planet to find out if life on Mars is possible. At first glance, the red planet, located only 7 months away from Earth, is completely unsuitable for habitation. Mars, on this planet, there are no rivers, no fresh air, no food. The force of gravity on the surface is twice smaller than Earth's, which would have an adverse effect on human health over time. The atmosphere there contains many gases toxic to humans, so an oxygen mask would be a must. A person would not be able to move around the surface without a spacesuit, due to the low atmospheric pressure and constant solar radiation. So how would the first people on Mars and the subsequent colonists survive in such harsh conditions? First, let's tackle the matter of oxygen. Scientists have already made significant progress in that direction. In April of 2021, Mars rover Perseverance managed to extract oxygen from the atmosphere, using a tool called MOXIE, by a process known as solid oxide electrolysis. In theory, MOXIE can perform the same function as trees on Earth. In the near future, since this kind of technology already exists, it's just a matter of scaling it up to meet the needs of the future colony. As for water, the vessel that brings the first colonists is expected to be equipped with an efficient system of recycling water, similar to the one on the International Space Station. This creates a little bit of freedom for the astronauts while they search the planet for potential sources of water. We know that in the early stages of development of the solar system, there was water on Mars. Previous expeditions have already found water as part of the mineral and soil composition. Currently, discovered and reliably confirmed volumes of water on Mars are concentrated mainly in the near-surface layer of permafrost, dozens and hundreds of feet thick. The majority of this ice is beneath the planet's surface, since it cannot stay stable in current climate conditions and quickly evaporates once on the surface. The only places cold enough for this ice to remain all year round are the poles, where the ice forms so-called polar caps. In those areas, the overall volume of ice is estimated to be 1.2 million cubic miles. For reference, the sum total of freshwater lakes and rivers on Earth only reaches 24,000 cubic miles. If the ice were to melt, it could cover the entire surface of Mars with a 115-foot layer of water. In 2018, after probing of the planet, the Marsis spacecraft discovered the presence of a subglacial lake on Mars. 1 mile deep under the ice of the South Polar Cap, about 10 miles in diameter. This became the first known permanent body of water on Mars. And in 2021, the ESA satellite ExoMars, capable of peeking into the depth of several dozen feet, discovered large deposits of water in the so-called Mars Grand Canyon. Currently, this is by far the most accessible water source on Mars, making the Vales Marineris Canyon network a good place for our first colony on the Red Planet. The supplies from a spaceship won't last forever, so the colony will have to make headway in growing edible crops. Scientists are very optimistic about this process because of the composition of the upper crust of the planet. Martian soil contains many of the nutrients that plants need to grow and survive, such as nitrogen, potassium, and phosphorus. Once we have a stable supply of air, water, and food, we will have built an excellent platform for building a colony from available materials. Martian soil can serve as a good material for building shelter, necessary to protect the settlers from solar radiation and dust storms. Of course, the technology most convenient to us would be construction with the use of mega 3D printers. This technique is already being used here on Earth, and it can prove itself quite useful in such harsh and limited conditions as on Mars. Of course, all the necessary provisions and equipment to create favorable living conditions for the first colony will initially have to be delivered by interplanetary spacecraft. But how do we get to this planet? Several projects to create suitable vessels are being developed as we speak, and the SpaceX Starship is currently leading in terms of progress. As of early December of this year, Starship will be launched on its first orbital test flight. The launch vehicle will be super heavy. A notable feature of this rocket is that the rocket itself and the ship are both reusable and can be refueled in Earth's orbit. Once the ship reaches its destination, it can be refueled using the natural resources present on Mars, water and carbon dioxide, which is very convenient for us. These factors greatly reduce the cost of production and the cost of transporting goods, respectively. The colony will also need a source of electricity to exist. Everything, even the basic things like the extraction of air, water, and food, will need electricity to function. Fortunately, Mars has huge reserves of deuterium. Deuterium, also known as heavy hydrogen, serves as a fuel for thermonuclear reactions. Imagine 0.034 fluid ounces of liquid fuel from heavy hydrogen can produce as much energy as 20 tons of coal. All we need to allow us to develop a colony are fusion reactors. Speaking of those reactors, quite recently, U.S. scientists have made a breakthrough in the field of thermonuclear energy. Scientists managed to obtain useful energy in a thermonuclear reaction. But the question remains, can this colony be self-sufficient? There will come a time when Mars will not need Earth to sustain itself. Much like the United States found itself long before the Revolutionary War. Does that mean that life itself will be self-sufficient? No, while we will be able to grow our own food on the planet in greenhouses, what about wild animals? birds, fish, rivers, oceans. Thus, in many ways, terraforming becomes a necessity. Terraforming is essentially the process of creating another Earth. The general consensus is that terraforming is required for global colonization, and global colonization is required for terraforming. These concepts go hand in hand. So let's break down the terraforming process into stages that could bring life on Mars much closer to terrestrial life. At stage 0, we, as colonists that arrive here first, can only live in spacesuits with a sufficient supply of oxygen. At this stage, we're faced with problems such as low temperatures down to negative 193 degrees Fahrenheit, an atmosphere full of toxic gases, very low atmospheric pressure, which compares to less than 1% of the Earth's atmospheric pressure, and of course, the cosmic rays penetrating everything on the surface of Mars. The thing is, Mars has little to no magnetic field, which could protect us from radiation. For reference, a person's exposure to radiation on Earth is 40 times lower. For the next stage, we'll try to get closer to creating conditions where it would be possible to leave the shelter with just the oxygen mask, without the need for a spacesuit. To do this, we need to take care of the radiation, temperature, and density of the atmosphere. Reducing the reflectivity of the Martian surface would allow for a more efficient use of sunlight in terms of heat absorption, which would warm up the planet's atmosphere. This can be achieved by spreading dark-colored dust from Mars moons, Phobos and Deimos, which are among the darkest celestial bodies in the solar system. The alternative is to introduce dark extremophile microbial life forms, such as lichens, algae, and bacteria. This way, the surface would absorb more sunlight, raising the temperature in the atmosphere. If algae or another type of flora took root, it would also introduce a small amount of oxygen into the atmosphere, although not enough for humans to breathe without assistance. In April 2012, scientists reported that the lichens survived and showed remarkable results regarding the adaptive capacity of photosynthetic activity during the 34 days of simulation under Martian conditions at the Mars Simulation Lab. That being said, Mars is already the second darkest planet in the solar system, absorbing over 70% of the incoming sunlight, so there's little scope for further dimming. Another problem with this method is the regular Martian dust storms span across the entire planet for several weeks at a time. Not only do they increase reflectivity, but they also block sunlight from reaching the surface. Once the dust settles, it sticks to whatever it touches, effectively obscuring anything previously deposited on the surface from the sun's reach. The terraforming of Mars would entail 3 major changes interconnected with each other: the creation of a magnetosphere, the creation of an atmosphere, and an increase in temperature. The atmosphere of Mars is relatively thin and has a very low surface pressure because its atmosphere is made up mostly of carbon dioxide. When Mars starts to warm up, CO2 can be helpful in keeping the thermal energy near the surface. Moreover, as it warms up, more CO2 from frozen reserves at the planetary poles should be released into the atmosphere, increasing the greenhouse effect. Another way to improve the atmosphere and subsequently create the greenhouse effect is the introduction of ammonia, methane, and other hydrocarbons. Large deposits of ammonia and hydrocarbons have been found frozen on small celestial bodies such as Titan, which orbit the solar system. It may be possible to redirect the orbital movement of these or similar small objects containing large quantities of the aforementioned substances, so they collide with Mars, thereby releasing them into the Martian atmosphere. However, even if we can find a way to prevent its release into space, methane can only exist in the Martian atmosphere for a limited time before it's destroyed. Presumably, this gas will eventually be depleted via the same processes that strip Mars of much of its original atmosphere. But these processes are believed to have taken hundreds of millions of years. Still, well-known compounds that we've been generating on our planet for many years can come to our aid. Particularly potent greenhouse gases such as sulfur hexafluoride, chlorofluorocarbons, or perfluorocarbons have been proposed as initial means of raising the temperature on Mars and maintaining long-term climate stability. These gases create a greenhouse effect thousands of times stronger than CO2. It has been estimated that approximately 0.3 microbars of these gases would need to be injected into the Martian atmosphere to melt the CO2-laden south polar glaciers. This is equivalent to about 3 times the mass of CO2 gases generated on Earth from 1972 to 1992, when their production was prohibited by an international treaty. Maintaining the temperature will require the constant production of such compounds as they're destroyed under the influence of the sun. It's been calculated that the introduction of 170 kilotons of optimal greenhouse compounds annually would be sufficient to maintain the greenhouse effect given the terraformed atmosphere. However, even with all of these efforts, it would be difficult to preserve the